Hello. So just to recap a little bit, uh, we just finished finding the MLE for exponential with mean theta. Here we have the likelihood function, and we reduce it here. For simplicity of computation, we now take the log of this, so we have little l y theta equal to ln ly theta, and we get, what did we get? We did this already, right? So we had minus n, right? Minus n ln theta minus n y bar over theta. And we then take the derivative, right, of that. So taking the derivative of that. Last time we found we had d theta l y theta equal to minus n over theta plus, because I have theta to the minus 1 power, plus n y bar over theta squared. Setting that equal to 0 leads to setting that equal to 0. I add the n theta to both sides, and I get y hat equals theta. Okay, one thing to point out here is that, so the MLE is again y bar. Did I say y hat? Y bar is the MLE for the exponential mean theta. Note again, y bar is a sufficient statistic, so and it's also unbiased. So we can also note that, because, note again, that y bar is sufficient. Can you see why? If we take, you actually get the factor, you can see the factorization usually because you have the likelihood right here. So you can see that you have this piece which has y bar and theta in it, and then this piece which doesn't have theta in it. So y bar is sufficient and unbiased, as you can show. So y bar is also MVUE. So it's minimum variance unbiased estimator, as well as being the estimator that we get from maximum likelihood. You won't always get an unbiased estimator, but you will always get a sufficient statistic when you use the maximum likelihood method. So, so let's write this down. It's true, so remark, it is true that MLEs are always sufficient statistics. The reason is that if a sufficient statistic exists, right? So if U is sufficient, then by the factorization criteria, which is if and only if, then we can factor the likelihood function is equal to G U theta H Y, where U is a function of Y, but this function over here, this G function, only sees Y through U. So taking the log of both sides, then we have Ly theta, the log of this one, is equal to ln gu theta plus ln hy. And maximizing this has nothing to do with this function h of y. Maximizing this function, maximize this, to find the theta that maximizes this is the theta that maximizes this term. So the theta which maximizes Ly theta also maximizes Ly theta is the same that maximizes ln gu theta. So in other words, I can throw away this term and just try to maximize gu theta. Okay, so it is a function of y only through u. Okay, so this is just something to note. When you do this and you see MLEs, you can say, well, that's a sufficient statistic. Okay, let's do another example. So, third example. Suppose I have y1, yn uniform 0 theta. And let's find the MLE. Well, let's write the likelihood down. L product 1 over theta. Let's see, 1, 0, yi. Yeah, okay. And we can multiply this out. So I have 1 over theta to the n, 1 yn, the maximum has to be less than theta, and the minimum has to be greater than 0. Yep, right? Okay, I don't think we need to take the log here. We need to find the theta that maximizes this expression. So one thing to note is that 1 over theta to the n. So what does this function look like? Maybe we can make a careful graph of this. So we don't want to, so let's make a careful graph of this. So look, if the minimum is greater than 0, if y1 is, if y1 is less than 0, the likelihood is 0. And if yn is less than theta, then the likelihood is 0. Otherwise, it's just 1 over theta to the n. So let me draw 1 over theta to the n. It will look something like this, right? This is the function 1 over theta to the n. Okay, so note 1 over theta to the n is decreasing on 0, infinity, and has no max on. Because it approaches positive infinity as it goes to 0. However, can theta go to 0? Can it be arbitrarily small? No. That's because of this restriction here. Sorry. Because of this restriction. Right? It must be bigger than the maximum sample. So if I think of this is the likelihood now, where this is, say, yn, the likelihood would be 0 here, then it would jump up here. So you cannot have a theta here. So if this is theta, and this is just the constant value yn from the sample, this is a picture of the likelihood function, Ly of theta. And you can see it's not maximum in any of these values. It's 0. Its maximum value is attained here. So we're saved, but because theta must be greater than yn, a maximum is achieved for the likelihood at theta equals yn. Okay. Notice again that if we go to the likelihood function, yn is part of this, the max of the sample. Factors, you might even remember from 9.4 that the max is a sufficient statistic for theta. So once again, we see the MLE is a sufficient statistic for theta. So note again, yn is sufficient. However, this time it is biased. Okay, so it's not an MVUE, but we didn't claim they all had to be MVUEs. We just claimed they had to be sufficient. The first two examples were also unbiased, so they turned out to be MVUEs. Okay, just one more thing here is the invariance property. So invariance property, we won't prove this of MLEs if theta hat is MLE for theta, then T theta hat is MLE for T theta. So I can use an MLE to estimate any function of theta. This is very useful. So, for example, we found that y bar is MLE for P in a Bernoulli P. So the variance of a Bernoulli P, so if we want to an MLE for the variance of y, where y is Bernoulli P, we take y bar times 1 minus y bar. Okay, so this is because var y equals p 1 minus p, and by the invariance property. Okay, thanks. That's all the time we have.